Hello and welcome to Hands-on Arduino, Part 4. In this discussion, we're going to talk about I2C communication. We're going to give a couple of examples of using I2C communication. So we're going to start off just giving a little quick rundown of what I2C is all about. We did this back in Lecture 11B. But I'm going to talk a little bit about it again just to kind of give you some more information about it. The I2C communication is also often called two-wire interface. So that's the non-proprietary version of it. It'll allow up to 127 uniquely addressed devices, up to 400 kilohertz data rates. That's not a typical data rate for it, but that is a possible data rate. The data rate in general is affected by the length of the line, the type of cable, and the pull-up resistor size. In terms of communication channels, when you communicate serially, you need some kind of a connection. So a two-wire connection is a good way. Here are some ways of actually making those connections. We can use an unshielded twisted pair. We can use a shielded twisted pair. We can use shielded and cable, not twisted, or we could use a coaxial cable. And so based on these, you may have various amounts of resistance and capacitance. The resistance and capacitance ultimately affects the bandwidth that you can use here. But for our purposes, any of these would work. So we're not too picky because we're not going to be going extremely fast in what we do, but you may want to push the limits of the I2C communication, and so you would want to choose wisely. Okay, so a lot of this also depends on how noisy your environment is, your operating environment. It depends on how the types of problems involved in your communication situation. So an unshielded twisted pair of cables is what we're going to actually use in our demonstrations today. It's just two wires, and you just twist them into a spiral kind of twist, all the entire length of the wire, the connections. Shielded means in addition to having that twisted pair, you also have foil that wraps around the entire thing for the whole length, and that at one end that foil is grounded. Okay, so shielded and cabled is basically the same as shielded twisted pair, except the pair is not twisted. And then finally coaxial. Coaxial is where you have a ground that's like a sheath, and you have the conductor. You have some kind of insulator in between there, and then the conductor going through the middle, and so that's one way of doing it. So for example, like cable TV uses a coaxial cable. So those are different kinds of connections that can be used physically. Here is again the I2C connection that we could work with. In general, you could have a master and a number of slaves. So notice we're going to have we have a microcontroller here, that's the master, and a microcontroller over here, that's the slave. And then you have these. So notice it's called two-wire interface. But what have I got here? Actually, I've got it looks like 4 wires. How does that work? I'm sorry, 3 wires. So it's not exactly two-wire interface. And actually, when we implement it, we're going to use 4 wires. Because it's also good to have a ground that connects everything. So it's called two-wire interface. Practically, you're probably never going to actually implement it using just 2 wires. So anyway, the point is that it's 2 wires are all that are essentially needed. And so anyway, so in general, you can have up to each device has a unique address up to address 7F from 01 to 7F. the master has address 0, 0, 0. And in general, you'll have a pull-up resistor for the data and the clock lines. So SDA is the data line, SCL is the clock line, and you'll have pull-up resistors. And the pull-up resistors will be somewhere between 1.5K and 100K. Generally, that's the ballpark you're going to be working with. So this bus is bidirectional, and each of the devices has an open drain. And so basically what happens is whichever device is communicating is actually pulling down. So it's actually, one of these guys is actually grounding the cable, and that's what makes it low. So this is more flexible than SPI communication, but it is slower in general. Now in the Arduino has certain things that it works with. So, and again, it has your clock line and it has your data line. When these come in, they go through these things. One goes through a slew rate control that's associated with the clock, and it also has a spike filter. So it has both of those. That goes into a bus interface, which detects starting and stopping. It recognizes addresses. It has an address match unit to make sure that things are, that it has a address that it can recognize. It has a bitrate generator. This is actually the rate at which the communication takes place, and of course control units that set the various registers. So that's the basic idea. In lecture 11, we actually went through all the registers and showed you what each of those registers are doing. We're not going to go in quite that level of detail in our hands-on here, but it's helpful to know those things. So again, each device could be a master, a slave, or both. Generally, if it's a master and a slave, it can't be both at the same time. It can be one or the other. Okay, so if you have two microcontrollers, one can be the master and the other slave, and then later on, the other can be the master and the one being the slave. Okay, so, and there's a whole protocol for how the communication goes, and I'm not going to go through all the details of that. That, again, is mentioned in lecture 11b. So here's the first problem. We're going to actually consider two problems, or two demonstrations that we're going to do with the I2C. First is blink. We're going to do a blink program. So basically, we're going to have one Arduino acting as a master. We're going to have another Arduino acting as the slave. And we're going to have the master communicate to the slave when to blink. Okay? And then the slave will blink upon command. So really, in this case, the communication is going only one way, from the master to the slave. Okay, so it's not two-way communication in this case. Communication can go both ways, but in this case, it only goes one way. So even when communication does go both ways, it can only go one way at a time. Okay, so it's not full duplex. Okay, so that's the problem we're going to look at first. Second problem is analog information. So again, we're going to have one Arduino as the master, the other Arduino as a slave. We're going to have a potentiometer connected to provide an analog input to the slave. So the slave is going to have an analog input coming in. And upon request, the slave reads the analog input and sends the value back to the master. So the master is going to command the slave to read the analog input, and then it's going to return the value back to the master. So that's the second problem. So those are the two problems we're going to look at. Let's now consider the first problem, the blink program. So here's the layout we're going to use. So I'm going to have two Arduinos, a master and a slave. In this case, for my demonstration, I'm going to have the master be Arduino Uno, and for the slave, I'm going to have it be an Arduino 2009 or Due Milanova, in case you're wondering how that's pronounced. My pronunciation is probably not perfect since I'm not Italian, but anyway. So here is the connection that we're going to be making. So we're going to be using 4.3K ohm resistors for the pull-up resistors. So we have these connections. We have 5 volt going to the top of this resistor, which is also connected to the top of this resistor. Then we have ground going to these 2 connections. We also have these connections, A4 and A5. What are A4 and A5? Do you remember what those are? Well, in case you have forgotten, we're going to go take a look real quick here at this diagram of the Arduino Uno pinout. And we see that A4 and A5 have as an alternate function SDA and SCL, so the clock and the data. Now, the Arduino Uno actually has the clock and the data over on this side as well, in these 2 pins. The Due Millenova, the 2009 version, does not have these 2 pins. So we're just going to ignore those 2 pins for now, even though we know they exist. We won't use them. We're going to use these pins over here. Okay. So coming back over, we have the clock and the data. So how did that go again? So the data is A4, clock is A5, and so data A4 here is connected to red, and then A5 here is connected to black. And notice that when we do a twisted pair, so this is a twisted pair wires. When we do the twisted pair, we always twist a signal with a ground. Okay, so notice these 2 guys are connected to ground. And so when we do a twisted pair, we don't twist 2 data signals. Okay, so the whole point of doing the twisting is to help prevent what's called electromagnetic interference. And electromagnetic interference often occurs when you have 2 signal wires right next to each other. So you definitely don't want to do a twisted pair with a signal wire. So if you're going to use a twisted pair, you want to have the signal twisted with a ground wire. Okay, and so basically having that ground wire is kind of like having a shield for that signal. Okay, and so in our experiment, we're going to use a 2-meter unshielded twisted pair, so 2 meters, 6 feet, just to kind of show you, just so we can see that this works over a distance. It doesn't just have, these 2 guys don't have to be right next to each other. Okay, they can be separated by some distance. And then you can see here, I have, notice that these guys go to their grounds. So actually, you don't need to ground them on this side. But, well, actually, you probably should ground one of them on this side over here. Anyway, I've grounded both of them. So notice I use this ground up here at the top instead of the one next to it. And the purpose of that is I'm going to come back later and use this other ground in the next experiment. So I'll need another ground. So that's the reason for not using this ground, for this experiment. That way we can keep as much the same as possible instead of having to change everything around in between experiments. Change as little as possible in between experiments. So this is the hardware setup that we're going to use. Okay, so I laid it out here nice and neat so we can see it clearly. When you try to look at it in actual hardware, it never looks, it doesn't ever look nearly as clean as it does here. Okay, and in the actual hardware, instead of this light blue, I'm actually using a white wire. It's just that white didn't show up very well on the slide here, so I used a light blue just to kind of help you see different colors. And the rest of these connectors are not necessarily the same color either. So here I show you different colors. I'm not necessarily using blue to do all that stuff. I may use other color wires to do those things. So that is our hardware setup. Now what about the software? So each Arduino has its own program. We have a master program. Here's our master program. And we have a slave program. Okay, so let's take a look at the master program. So first thing we're going to do, and so notice this, the master is on our Uno. We need to include the library wire.h. So wire.h does the I2C communication. So there's a library that takes care of all the bit twiddling, setting of registers, and all that kind of reading registers, all that kind of stuff that's needed. So we could actually get down to that level of things, but for now it's probably just as well to use the library. Okay, so the library in this case, in the case of I2C and SPI communication, the library saves a lot of headaches. Okay, and so since there's a library already available, I highly recommend using it. Okay, so if you wanted to really push the envelope of things, then you'd want to get down and actually do the functions that the library is doing. But here, since the library is so freely available and the documentation is very clear on the Arduino site, then we're just going to use the library. Okay, so in our setup program, we only have two functions. We have the serial begin, and the reason we have serial begin is because we want to use the serial monitor. Okay, then we have wire begin, and notice we don't specify a bit rate. The bit rate there is a default bit rate, and we're just going to use that. Okay, so that's all that's in the setup routine. The loop routine now basically is what we're going to use to tell the slave to toggle, to turn on or off the LED. In this case, we're going to use on the slave the LED that is on pin 13, so we don't actually have to do any additional hardware on that side. Okay, so in our loop program then, so what we have a while statement, and that while statement goes all the way actually down to here. So within the loop, there's only a while statement. Okay, and the while statement says while the serial is available. Okay, so that basically checks to see if there is data coming across the I2C communication line. Okay, so if it is, then we're going to read that. We're going to do a serial read from that. Okay, so the wire library includes these functions: serial begin, serial available, serial read. Okay, and it's going to read the character, the first character. Now, if that character is equal to the capital letter H, we're going to begin a transmission. Okay, so we're going to begin a transmission, and in this case, our slave Arduino does not have a predefined address. So we're going to assume the address is address number 5, just to pick a number. You could have picked 42 or whatever. It doesn't matter as long as the slave identifies itself as number 5. Since this is the master is automatically set to be 0, device number 0. And so, incidentally, using the wire commands, a lot of these details are kind of hidden from us because they're taken over by the wire library. So we don't have to worry about them. So, if C okay, so on the serial monitor, this is actually on the serial monitor, not the wire. This is the serial monitor. Okay, so it's going to read a character. So if a character comes in on the serial monitor, okay, sorry about that. I was confusing there. So if that character on the serial monitor is the letter H, capital H, then we're going to do the I2C communication. So we're going to begin transmission to device 5, and we're going to write the letter H, and then we're going to end transmission. So it's very simple. We're going to simply write one word or one character, and it's the letter H. Okay, so again, in our serial monitor, we're going to enter a letter. If we entered the letter capital H, it's going to do this. Okay, if instead, if we use the capital L, then the program's going to do something else. It's going to write to 5L, and then it's going to end transmission. So there are only two symbols we can send to device number 5 that it will understand, H and L. So H obviously is going to turn the light on, and L is going to turn the light off. That's the basic idea. So that's the entire program that we're going to use on the master side. Okay, simple, nice. The slave is a little different. Okay, so let's see what's going on with the slave. So again, the slave code is what we've got on our Due Milanova. Again, we include the wire library. Then in our setup command, we actually have a little bit more going on. We first do wire begin, and in doing wire begin, we're establishing this device to be device number 5. So this is how we establish this Arduino to be device number 5. And device number 5, being a slave, is expecting to receive data. And so we need to define, in a sense, actually, this is actually like an interrupt service routine. We need to define the name of that interrupt service routine. In this case, it's called receive event. Okay, so here it's actually kind of an interrupt service routine that's kind of disguised, but that's actually what's going on. It actually is using an interrupt service routine and has a particular name. Now, so we also are going to set up pin mode pin 13 as an output, and we're going to start it off low. So we're going to start it off, the light off. Okay? Our loop program has nothing going on. So in other words, what basically is going to happen is our slave Arduino is basically going to just be sitting there waiting for an instruction from the I2C. So when a receive event occurs, it's going to go to this interrupt service routine. Okay, so that's all that this program is doing. So now let's look at the interrupt service routine. So here's the interrupt service routine, and notice the interrupt service routine has the input argument how many. Okay, so that is how many characters or symbols are coming across. Okay, so by default, it's well, when you send something, when you send a serial string of things from the master, it's going to buffer the data. Okay, and when it's buffered, when the end transmission occurs, it counts how many things were sent, and that's what comes into this variable how many. Okay, so notice we didn't actually define this variable anywhere, so you pretty much just kind of need to leave this command alone. Don't touch it. Okay, so that's kind of one of those magic formulas, which I generally try to avoid, but anyway, here we use it. So now within our interrupt service routine, we have a while loop, and in that while loop, notice that we're basically checking to see if something has come across. So when something is available, we read a character. If the character is an H, then we do a digital write high. If the character is an L, we do a digital write low. And so this is the code that's required to do the I2C communication. Here is our Arduino master code. Here is our Arduino slave code. And over here, we have our master Arduino Uno, and we have our slave Arduino hooked up. Okay, so this is the connections. These are the connections that we're working with. Okay, and so I have a battery here that I can use to set up power for the slave Arduino. Okay, so that the USB cable can be used for the master cable, while this power can be used with the slave Arduino. I have these things taped down to this board because one of the most frustrating things about doing hardware is the mechanical side of things, not the electrical part. The electrical part is pretty straightforward. As long as everything is connected right, it pretty much works. But a lot of times, the mechanical stuff, things start, the little connectors pop out and all that. Frustrating. So I have everything taped down to kind of help keep a lot of that frustration down. Here you can see I have these twisted pairs of cables, wires hooked in there, and so I have the breadboard here has my resistors and these jumper wires and so forth. So there's the hardware. Over here is the software. So here's my master code, and I'm going to first program my slave. So notice that my slave is a Due Milanova, which is different than the Uno. So I need to go and I first need to set my Arduino to be a Due Milanova. Then I need to set my USB port properly. Okay, so if you use two different processors, you need to go back and check. Otherwise, when you try to build this and compile it and send it on there, it just won't go, and it's frustrating. But that's why. Okay, so it's loading now. It's loaded. Okay, done uploading. So now I can hook up the power to that one and the USB to this one. I go through and I need to again change the board to an Uno and the serial port to its correct USB connection. So I'm using a Mac, so Mac has a different set of connections. On a PC, it's like COM this and COM that, but on a Mac, it actually says USB this or USB that, so a little bit different. Okay, and now I can load this on. So it's uploaded. So now it's theoretically running. How do we know if it's running? Well, let's pull up our serial monitor. So remember, in the serial monitor, I need to enter an H to make the thing go high. So I'm going to type in an H, enter, and boom, goes high. I'm going to type in an L. Boom, turns off. H on, L off. Boom, it works. Sweet. Cool. We now move on to our second problem, that of analog communication. Here's the layout that we're going to use for this. So in our layout, we have basically the same configuration as we had before. Over here, this is exactly the same, but the only difference now is we have this potentiometer here that we connect up to. So we have 5 volts and ground, and then we go into analog channel 0. Okay, so analog channel 0 is what is going to read our analog voltage, and so here's the layout that we have. And otherwise, we have the same data and clock as we had before. So just a minor modification allows us to have this new configuration. So that's the layout. That's the physical plant. Moving on to the software, we first look at the master. In the master, again, we include the wire.h, and now I'm going to define this global variable volts. I could define that in the loop, but I choose to define it there. Again, I begin both the wire and the serial. Okay, so that's the I2C we begin, and also the serial we begin. Now, in this program, we are setting the thing up to communicate from the slave to the master. And so here's how we can do that communication. Actually, there are a number of ways of doing this. It's actually there's actually a number of ways. This is one way of doing it. This is kind of a standard way of doing it. So I want to do it this way. We wire begin transmission, and we identify which device we're going to use. Again, we're going to call our slave device number 5. And then I'm going to define here the variable available. Having defined that, then I am going to do a request from device number 5 2 bytes. Okay, so what is returned from this command is the number of bytes that are actually available. Okay, so if you try to do this command, you might get 2 bytes, or you might get something else. So remember, when we read the analog input, we're getting 2 bytes. So that's why we want 2 bytes here. Okay, and so if in fact we do get 2 bytes, then each if we get 2 bytes, then each wire read reads in a byte. Okay, and so if we use this command, volts equals wire read, and we do a wire read twice, then we shift the one wire read over 8 bits, and then we OR it with the other wire read. So this one actually reads first, and then this one reads, and then this puts it all together into a single 2-byte value called volts, and then I will print out that value. And so if it's available, then it will do this, and then we will end transmission, and we'll wait half a second for the next reading. And so notice that I have this if. It's possible that you don't get 2 for some reason. You could also have an else in here that would display something if for some reason you got a different number of bytes being sent. For example, if 1 byte was only available, then you could display an error. Okay, so this is one way of checking. You can do some error checking in all of this. So as you can see, the master in this case is pretty straightforward. Let's move on to the slave. So the slave is, again, it's fairly simple. We have basically the same setup and loop programs as we had in the previous example. The difference now is we have this our interrupt service routine, our void, our request event routine. I'm going to read the analog value, analog channel 0. Okay, notice I've defined this byte C having 2 values. Okay, so C0 is going to be the high byte, C1 is going to be the low byte, and then I'm going to do a wire write of C. So it's going to, so when you do a wire write, and if you write data, it's going to assume an array, and this value here, 2, tells you how many elements in that array are getting sent. Okay, so that's how the wire write works. And so this works in conjunction with the wire read. So this sends 2 bytes. The wire read reads 1 byte at a time. Okay, and so if I set in the high byte and the low byte this way, and I use that in the master, if I use that code to do the appropriate shifting of bits, then I get the proper transfer of the correct transfer of the data, okay, the values that we're working with. So that's the code. Let's move on now to look at the program running. Okay, here we have our code set up. We have our master program, and we have our slave program. And over here we have our master that's connected. Here are the resistors that are used for the I2C interface. Over here, so here's our twisted pairs. There are two twisted pairs. Here's the other sides of those. Again, this is 2 meters long, so you don't get to see the entire length, but you'll have to take my word for it that it's 2 meters long. So again, I have this Arduino connected up with a battery, so it has already been programmed, and we have a battery that's running with it. Here's our potentiometer that is used to provide the input voltage that we're going to be using. And so now I'm going to come over here and look at the serial monitor. And so now I have the value 0. So I'm going to turn this and I can see the value updating. And it goes all the way up to 1023. So it's actually correctly reading the voltage from the potentiometer. Gives us a voltage between 0 and 1023, and it's doing so by communicating that value across the I2C channel to the master from the I2C. Sweet. So we have now done 2 different forms of communication, one way and one the other way. One where the master sends information over to the slave, and in this case, when the slave sends data back to the master. I hope you've enjoyed it. Thanks for watching.